Okay, I've been asked by the Promise program to give this entire lecture in limericks. But I actually don't find myself really up to the task. So instead, I'll recall the situation. We have a semi-simple representation, a semi-stable representation, irreducible, modular. K is basically the prime field with p elements, where p is an odd prime. Although, as we see in and out of the lectures, it's often convenient to have other finite fields in the picture, even if you're only interested in the case of the representation defined by a semi-stable elliptic curve over Q. And we are considering deformations. More precisely, we are considering deformation problems. And these deformation problems are problems which we hope are solved in the sense that Udi alluded to at the beginning of his lecture this morning by modular forms of weight 2. And a typical such deformation problem is called D. D represents a set of local conditions. And as I've explained in the last lecture, D really amounts to giving some finite set, which we didn't actually name. This is a finite set which tells you those primes of Q at which you allow unrestricted ramification. And in this language, there is the notion of the minimal deformation, and the minimal deformation corresponds to the empty set. And what we've seen in this morning's last lecture, the 10:30 lecture, is that we can solve the problem with this empty set. Namely, we have a kind of fundamental conjecture which we have to solve if we want to embrace all semi-stable elliptic curves over Q. The fundamental conjecture is that if you take the universal deformation ring attached to this deformation problem D, and you look at the natural map onto the Hecke algebra T sub D that I defined in my lecture yesterday, the conjecture says that this map, which we could call phi or phi sub D, a priori a surjection, is in fact an isomorphism. And this says qualitatively that every deformation of type D is modular, and then when you make things precise, you see that elliptic curves which are semi-stable over Q and whose p division representations give you rho bar are themselves modular. And at the same time, we have some possibility of considering simultaneously different deformation problems for varying finite sets. Maybe I should just say in this part of the board what I said orally, namely that the conjecture is now established from the point of view of this conference. The conjecture is now proved for the minimal deformation. And the problem is to think about non-minimal deformation problems. Let's get an eraser. Behind me. Great. And the problem is to pass from one D to another. So what is the situation? We can have some sort of notation for this. We could have two deformation problems D and D prime. And we could say that one is contained in the other if various trivially equivalent things are true. One is that every deformation of type D will be of type D prime. And the other is that the set, finite set corresponding to D, is contained in the finite set corresponding to d prime. In other words, relative to d, d prime has more unrestricted ramification. So that's what we'd like to do. We'd like to think about pairs d and d prime. And of course, the theorem which you can anticipate the desired theorem is that if phi sub d, now I put in the subscript, is an isomorphism, or injective, well then, so is phi d prime. This is true if we allow that d is contained in d prime. Now, there's an obvious diagram that goes with this. We have the map phi sub d prime. Maybe we just call that phi prime. Try to eliminate the subscripts script d, which are hard to write anyway. So we'd have an r prime mapping to a t prime. This is what happens for the wider deformation problem. And we have a map r mapping to t for the stricter deformation problem. This would be called phi. This would be called phi prime. And there are some maps in the picture which make the diagram commutative. First of all, the fact that every deformation of type d is a deformation of type d prime means that the universal deformation of type d is a deformation of type d prime. And that gives rise to a map like this. At the same time, from the construction of Hecke algebras, which are basically made from classical Hecke algebras of levels that depend on d or d prime in these situations, we know that there's a map from t prime to t. The best way to think about that is to remember our former notation for prime, namely to remember that when we define these Hecke operators and Hecke algebras, we could really make things go just by considering operators prime to the level and prime to p. And then there's really a compatibility of definition. Every tn here will just map by restriction to the tn at the lower level. And the one thing that is convenient to know, which is only slightly less than obvious, is that the right-hand vertical map is a surjection. In other words, this tn can be thought of as generated, this t prime can be thought of as generated by operators, let's say with prime index, which do not divide a certain level. And t is generated by operators which do not divide some smaller level. And it's possible that some of the generators of t have no counterpart among the generators of t prime. Nevertheless, it's a really easy lemma to show that if you throw out some Hecke operators from t or t prime, you don't change the algebra. So this map is a surjection. In fact, we call this map alpha in what follows. And if you want to prove this, the normal thing that you do is you proceed along some sort of induction path, namely the plan of attack would just be to pass from d to d prime by allowing for the first time in d prime, but not in d, unrestricted ramification at some prime q. Let me just write on the board where we do this. We allow this to happen in the deformation problem d prime, but not in the deformation problem d. Now, the idea is that if you can, let me just say it again, if you have some way of relating the problem at the lower level to the problem at the higher level, and you're trying to prove the isomorphism up top, what you can do is just have this relation and then sort of parachute to safety and let someone else, for example, someone working in the minimal case, establish the isomorphism at the lower level. So that's the plan of attack. And if you think about what this prime q can be, the simplest way to fix on what's going on is to imagine the application that you have in mind. So the application that you have in mind is that you're trying to embrace once and for all the p-adic representation coming from some semi-stable elliptic curve over Q. So this is mapping to GL2 ZP. Its reduction is rho bar. And the point is that it's possible, because some ordinal of a minimal discriminant might be divisible by p, it's possible that rho EP has bad reduction at a given prime q, whereby rho bar, for some circumstantial reason, happens to have good reduction at that q. If q is different from p, that means that rho bar is unramified at q. And here, of course, rho will be ramified at q because the elliptic curve has bad reduction at that prime q. So this is what you're trying to do. You're trying to pass from one to the other. So q would be some prime at which E has bad reduction, but where rho bar is finite and flat. If we think of q different from p, just to fix ideas, then you're really talking about the case where rho bar is unramified at q, and rho is ramified at q. So in that case, the unrestricted ramification really amounts to the following thing. As I mentioned in my previous lecture, if you want to think about this representation, you have to allow all modular forms when you build up the Hecke algebra, which have up to q squared dividing the level. Whereas, of course, here you're talking about modular forms which have level prime to q. So secretly, what you're trying to do, if you add q to d prime, not having it in d, is you're trying to pass, in some sense, from level n to level n q squared. Now, let me next talk about the strategy of proving this in terms of Selmer groups. If we think now about one of the Hecke algebras, say T as opposed to T prime, there's a map from R to T. And one of the two criteria which have been explained by René Schrolf for proving that T is a complete intersection is to think of this diagram as some diagram of pointed O algebras. Now, what's going on here? Well, you can kind of secretly imagine, and let's assume it for the purposes of exposition, that O is ZP. This map, the right diagonal map, is gotten from some modular form of minimal level, which represents the representation rho bar. We might think that F has coefficients in some number ring, which then localized at lambda actually just gives us ZP as opposed to some finite ring extension of ZP. And in this diagram, there is a kernel, which we can call Gothic P. And there also is, in the criterion that René called the Wiles-Lenstra criterion for complete intersections, associated to this map F, there's going to be some invariant eta, which we can think of either as an ideal of T or by pushing it down to O as some ideal of O. And the criterion is that T is a complete intersection and phi is an isomorphism if and only if the order of p mod p squared is finite and is bounded from above by the order of what I'll just call O mod eta. And this is some ideal. I don't know, I don't remember whether this was explained before, but this is an ideal which governs congruences between F and modular forms other than F somehow in the space of modular forms in which F lives. And on the other hand, this is an isomorphism if and only if we have equality in this inequality. At the same time, there is a Selmer group theoretic interpretation for p mod p squared, namely p mod p squared can be thought of as some h1 relative to this deformation problem D of the Galois group of, well, what Barry called QS, operating on some adjoint representation, but thought of not as a representation over FP or even as a representation over ZP, but rather you take this representation and you take, so to speak, the inductive limit of its finite quotients. Namely, you take some representation, for example, the p-adic representation coming from the modular form F, and you consider the adjoint representation for this Galois representation, maybe rho sub F, and you tensor it with QP mod ZP. So this is some way, I think I have that wrong, there's a ham somewhere. Let's see which way I want to write it. Yeah. Okay. So this is not the p mod p squared itself, but a group which will have the same order, namely ham from p mod p squared into qp mod zp. Okay. So imagine that you have proved that T is a complete intersection and that phi is an isomorphism. Here's phi in the case of a given deformation type D, and you want to pass from D to D prime. Then you have at your disposal a certain equality involving two different algebraic invariants, and what you want to do is you want to prove the corresponding inequality in the case of D prime. So you would then have a ring R prime and T prime, a corresponding kernel which would naturally be called P prime. And what you have to do is you have to prove two inequalities. Namely, in order to make things work, what you'd like to do is you'd like to prove that p prime mod p prime squared, and when I write this, I'm really thinking of its order. Let's try to put in the sharps. You want this thing to be bounded from above by a certain constant, which will be made explicit, times the corresponding order at the lower level. That's the first thing that you want. And the second thing that you want is that when you take the O mod eta prime would be the analog of eta for the algebra T, T prime rather. You want this to be greater than or equal to the same constant times the order of O mod eta. Now, if you have these two things, then of course you can continue, for example, the inequality on the top in the obvious way. Namely, you can just say that this is less than or equal to C times the order of O mod eta. That's because you know the isomorphism at the lower level. But then C times O mod eta will be less than or equal to the order of O mod eta prime. And since O mod eta prime is then bounding from above the order of p prime mod p prime squared, you will have the inequality that you need to establish that phi prime is an isomorphism and that T prime is a complete intersection by the criterion which was explained in René's first lecture. So what you need to do is you need to prove two things, and you want to do this for the same finite constant C. Now, when you do this, when you start thinking about this problem, you realize that p mod p squared is some Selmer group where you have a certain number of local conditions, and p prime mod p prime squared is the analogous Selmer group where exactly one local condition is omitted. So this means that if you go and you think about bounding p prime mod p prime squared in terms of p mod p squared, again I'll put in the order, there's a factor that comes in, and the factor is going to be some h1 of a local Galois group operating on the appropriate space. And if you pursue the computations in the style of Larry Washington's lecture, and in particular if you use local Tate duality, this h1 can be seen to be bounded, again from above, by an appropriate h0, and this is going to be h0 of the Galois group of fq bar over fq. So maybe we could just write h0 fq as in Udi's last lecture. And then this is going to be operating on the space which I've already written down, except you want to take its dual in the sense of Cartier duality, and then using some Weil pairing, you see that this is just the space that I've written down twisted once. So this is going to be ad of rho, but tensored with qp mod zp. And what is rho? Rho is going to be the p-adic representation attached to this chosen modular form f, which exists because we have the hypothesis that rho bar is modular, and then we can refine weight and level and so on. And if you calculate this h0, the only thing that's operating is going to be just some Frobenius element. And what will happen is that you get an inequality of the desired type. And here, what's going to happen is that C is going to be the order of Zp modulo a certain number. Well, I'll just call it n for number. In other words, C is going to be the p part of this number. And the number that you get is just going to be the product from I equals 1 to 4 of alpha I minus 1, where what is alpha I? Alpha I runs through the various eigenvalues of a Frobenius for the prime Q in this representation, the adjoint representation of rho. Now, there are two things wrong with what I've written. First of all, I'm missing a parenthesis. And secondly, I said, but didn't write, that this has to be twisted once. In other words, the eigenvalues in question have to be written, have to be multiplied by Q. And what are the eigenvalues in the adjoint representation? Well, they're just various ratios of the two eigenvalues of Frobenius in the initial representation rho. And those eigenvalues have product Q. We are dealing basically with representations whose determinants are the cyclotomic character. And the sum of the eigenvalues is A sub q being the qth coefficient of the modular form f. And if you work out what this is and just keep track of the constants, you'll see that this product is nothing other than q minus 1 squared times the product of aq squared minus the quantity q plus 1 squared. So it's a funny number which may strike you as being completely bizarre the first time you see it. When I say equality, these may not actually be equal, depending upon how I've written it. They may be equal only up to sign. But of course, the only thing that matters is the ideal that this generates in Zp. Now, this is just a little computation that you can do with the eigenvalues for the modular form f. And now, let me try to explain qualitatively what has to be done. Okay, let's bring this one down. Well, you see now what our problem has become in order to do this induction step. And here we're just adding a single prime q that didn't appear in the level of F before we started thinking about d prime. What the problem that we're doing has become is simply that of showing that if we consider O mod eta prime, that this is greater than or equal to, well, the O mod eta times the constant that I've written before, and that constant is q minus 1 squared times aq squared minus q plus 1 quantity squared. And it's not so much this constant that we want, but rather its p part. One succinct way of writing that is to take the p-adic absolute value of that number and then take the inverse of that, because the absolute value of p is 1 over p. So this is the thing that we need. And of course, if you start thinking about this in some qualitative way, you will start muttering things about congruences between modular forms. The point is that at level n, let's say that the deformation problem d corresponds to level n, and the deformation problem d prime corresponds to level nq squared, you have a certain number of congruences between f and the other modular forms at the same level, and that is governed by O mod eta. And what you want to show is that there are quite a few more congruences at level nq squared. Namely, you want to see somehow that this factor governs the congruences between f and forms that didn't spring up until you allowed q into the level. These would be forms of level q and or forms of level q squared multiplied by n. So the idea of this in words is that you need to prove congruences. And before this problem was considered in Wiles's chapter 2, some version of it was considered by Nigel Boston and other people who were thinking about deformations of representations and how they change by adding primes to the level. And if you want to make this a little bit more precise, if you want to see a bit more algebraically what it is that you have to do, you can introduce what people have called the relative Ada invariant. Namely, you have this map between Hecke algebras, T prime to T. And this map previously was vertical, and I called it alpha, one of the earlier boards. This is a map between Gorenstein rings, and you can certainly define an Ada invariant exactly as the original one was defined. Namely, you can take, for example, delta, choose an isomorphism between T and its ZP dual, and similarly do that for T prime. That enables you to define a dual to alpha, which we could call alpha dual or alpha check. And then delta can be taken to be alpha check circle alpha of 1. Then you get an element of T prime, which is well defined up to units. And what you want to do, of course, is take this element and first push it down to T. That's the first place where it will really become relevant. And then, of course, T has a quotient O, which is usually written below it, but let's just sort of write it like this. And you're basically thinking about the image of delta in O, which we could maybe just by abusive notation call delta once again. And then the formula that you get, which is kind of perfectly transparent if you use the Gorenstein property to define these Ada invariants just by taking maps and their duals. The formula which is transparent is that Ada prime is equal to delta times Ada. This doesn't make very good sense unless you pass to some common ring where all of the things are defined. So, for example, we could allow these things to live in T, which is the highest place where Ada will live, or where we need it is in O. So why don't we just say that this formula holds in O? And this is a formula involving three ideals of O. O, of course, is ZP. or if you prefer, it's a formula involving elements which are only defined up to units. And then, of course, what you want to do to reformulate things, you need to show that the order of O mod delta is big, and that's another way of saying that delta, thought of in O, is inside of an ideal, and that's the ideal which is generated by this number q minus 1 squared times aq squared minus q plus 1 squared. So this is the thing that you need to do. Now, before all of these representations get erased, one thing that I will point out is that there's been some back and forth at this conference between considering representations of fixed, meaning cyclotomic in practice, determinant, or representations with varying determinant. And the difference between the two is that when you fix the determinant, you get the trace zero matrices at 0 as opposed to the full four-dimensional matrix algebra. And what happens is that if you want to consider deformation problems with fixed determinant, one of the eigenvalues disappears from ad rho, and that's just one of the eigenvalues q. So if you fix determinant, then what happens is that in computations that you do, q minus 1 squared gets replaced by q minus 1. Okay. So what you have to do is you have to prove something about the relative Ada invariant. I'm now completely trapped. So here we go. And doing that, at least in spirit, is a problem involving congruences. And let me explain how one can visualize this relative Ada invariant, which we call delta. From the point of view of Hecke algebras of different levels. So let's just imagine that we have defined this Hecke operator T as being a subalgebra of some sub-ZP algebra of some partial product. It's a product of completions of various integer rings of modular forms. The modular forms are G, and we complete them at appropriate primes mu dividing P. So this is a product sign, not a Hecke algebra. And this is a product over appropriate pairs G mu. But the main thing that happens here is that the level of G is a new form whose level is dividing n. And if you think about T prime, you have T prime, which is contained inside of a similar product. I won't write all of the notation, but the salient thing is that the level now divides q squared n. So the level could be a divisor of n, but on the other hand, it could have a q or a q squared in it. And from that point of view, the surjection from T prime to T is just a surjection which takes T prime and projects it onto its image in a partial product, namely the product corresponding to the forms which don't have any q in their level. Now, it doesn't take too much imagination to start playing with this product. And in particular, you could define T double prime, just to give it a name. You could define it to be the image of T in the product of the completions OG mu, where now the level of G is constrained to be divisible by Q. On the other hand, it will be, since we're talking about a projection, it'll be a divisor of Q squared n. So we take exactly those factors which don't appear when you define T, and then what happens, kind of trivially, is that T prime is caught in a product of two rings, T cross T double prime, and it will be a finite index inside of this product. Up to finite index, these algebras are just really going to be products of these OG mu's. Of course, as always, we take G's only up to Galois conjugation, and we only take the mu's that induce the maximal ideal on the uncompleted Hecke ring T, or T prime, that we had. There's too much notation here. And we're in a situation where the two projections from T prime onto T and T double prime are surjective. And one thing that I learned from reading Lenzer's version of the Weil's criterion for complete intersections is that one way to view this relative Ada invariant, in this case delta, is to think of delta as being the following ideal of T prime. Namely, what is it? Well, in Lenzer's criterion, this is going to be the annihilator in T prime of the kernel of the map from T prime to T. That will just be the intersection of T prime with T double prime. And that annihilator consists of things in T prime that actually live in the first factor. So a way of looking at this is that this is, in fact, going to be T prime intersect T. And a way to think about this is that this is the kernel of the map from T prime to T double prime. Now, once you have that kernel can be thought of either in T prime, or you can think of it with no loss of information as an ideal in T. The reason for that is that if you have an element of T prime which is inside T double, which vanishes in T double prime, if it vanishes also in T, then it's 0. So anything in this kernel is in this intersection, and this intersection can be thought of as an ideal either in T or in T double prime. If you want to think of it as an ideal in T, what is it? Well, it's the ideal of Hecke operators at level n, which are the restrictions of Hecke operators at level q squared n, which vanish at on the forms which have q in the level. Well, that's a very long-winded way of saying in words what I've just said in symbols. And that's what delta is. It's some sort of obstruction phrase. You can phrase it in different ways, but one way to think of it, maybe qualitatively, is that it represents the obstruction for between. It's the obstruction of T prime from being the product of these two algebras. And if you try to say that in words, it represents the way that forms of level divisible by q and forms of level not divisible by q get messed up together. And it's a algebraic way, in fact, of measuring congruences between those two types of forms. Okay. And now the question is, how do you prove what is needed? Namely, the thing that you want, let me just write it here, is you want to show that delta is rather deeply contained in T. For example, if T were if T were literally the product, then delta would be the trivial ideal. And what you want of delta is that it should be contained in an ideal which, when pushed down to O, gives you this q minus 1 squared times aq squared minus q plus 1 squared. And if you work with forms without character in their level, as we're doing, the natural element of T, which will push down to that, is the element which is q minus 1 squared times some expression involving Hecke operators. And what is that expression? Let's bring this down a little bit. That expression is simply the 1 plus q squared minus tq squared. And now the question is, how do you do this? How do you prove such congruences? How do you prove that delta is small? And the method that Wiles uses is an adaptation and a generalization of a method which, in fact, I introduced in a 1983 article. And what I was trying to do is exactly prove congruences of this sort, not between level n and level nq squared, but more simply between level n and level nq. And what turns out to be the case is that there's a natural way in which this idea with the 1 plus q squared minus tq squared comes in. And it's kind of the obvious answer for what delta should be. And then what you have to do is you have to work a little bit to prove that this obvious answer is actually correct. And the method is really torsion point theoretic. One could say that it's cohomological. But the way that I like to think about it is in terms of Jacobians of modular curves. So let me now introduce the 2 or 3 modular curves which are appropriate to this situation. There's certainly x0 of n if d corresponds to level n. There's going to be x0 of qn since we do have some forms of level qn, but the real thing that we need is x0 of q squared n, which is the modular curve that is naturally suggested by d prime. And what you'd like is to have some geometrical realization between these two, relationship between these two curves. Now, as we have seen in a couple of the talks, there are natural maps called degeneracy maps between modular curves of a given level and modular curves of a lower level. And in fact, what happens here is there are naturally 3 maps from x0 q squared n to x0 of n. And in terms of the problem involving elliptic curves and subgroups, which the problems which are represented by these 2 curves, it's very easy to sort of see some form of these maps. For example, well, just to say it barely, if you have an elliptic curve with a cyclic subgroup of q squared n, there are 3 possible ways that you can get out of it an elliptic curve with simply a subgroup of order n. One way is simply to forget the q squared part of n. Q is prime to n. And another way is to take a subgroup of order q or q squared and divide by it and see what happens. Also in terms of the upper half plane, it's easy to see these maps. So they're kind of well-established degeneracy maps, and they will induce by one of the 2 functorialities of the Jacobian a triad of maps going from j0 of n to j0 q squared n. And if you think about what's happening at the level of cotangent spaces, if you think about what's happening at the level of modular forms, you'll see from one point of view or the other a map from 3 copies of the space of cusp forms of weight 2 on gamma 0 of n toward the space of weight 2 cusp forms of level gamma 0 nq squared. And this map turns out to be injective. You see that on the way to thinking about the theory of new forms. And the fact that this map is injective can be traced back to the fact that this map, well, I haven't really said yet what the map is, but you can assemble these together to make a map from a product of 3 copies of j0 of n toward the big Jacobian. And this map, a priori, is not injective, but it turns out that it has finite kernel just because on the level of cotangent spaces or tangent spaces here, you'll just get an injection of Q or complex vector spaces. So this is a map which has a finite kernel, and it turns out to be very important if you want to prove congruences to figure out something about this kernel. The problem that I considered analogously in 1983 was a problem where you had j0 of q squared n, and it was receiving analogously 2 copies of J0 of n. And what I proved using some results of Ihara is that this map is essentially injective in the sense that its kernel is a well-known subgroup of J0 of n. It's the so-called Shimura subgroup, which is the kernel of a natural map from J0 of n to J1 of n. And in particular, its kernel is Eisenstein. That concept was mentioned, for example, in Thiluin's talk. And it has absolutely nothing to do with irreducible Galois representations. And in particular, it'll have absolutely nothing to do with rho bar. So from the point of view of our analysis, our Hecker rings are really already completed at these maximal ideals, which pertain to rho bar. It's as if this map is an injection. And similarly, what Wiles proves is that if you pass to m divisible groups, then you will get from this diagonal map literally an injection. So things behave as though this map were an injection, and maybe we could just sort of cheat and say that we get an injection of abelian varieties. And now the question is, how do you get congruences knowing that this map is an injection? Well, let's bring this up and bring this down. Let's maybe keep this up. Well, the idea is the following. We will have inside of J0 Q squared n, which is an abelian variety which is endowed, well, before completion with an action of T prime. And if you want an action of T prime after completion, you should pass to m prime divisible groups. But just imagine that we're on the level of Z Hecke algebras. T prime will act on this abelian variety, and the T will act on the subvariety, which you get by considering 3 copies of J0 of n. In other words, on this abelian subvariety of the big Jacobian, the action of T prime factors through an action of T. And once you have this abelian variety, you can pass to what you might call the orthogonal abelian subvariety of this big abelian variety, call this thing J. The point is that if you dualize the inclusion of A into J, you will get a map from the dual abelian variety to J to the dual abelian variety to A. And to define the orthogonal, all you have to know is that J is its own dual, so that you really have a map which is going to be a surjective map between abelian varieties whose kernel is connected, whose kernel is an abelian variety. You will get a map which is dual to this inclusion. And if you let B be the kernel of that map, then you have an abelian subvariety of J, call it B, with a property that the intersection of A and B is some finite abelian group, and J is filled up by A and B. Now, in other words, what's happening is that J is isogynous to the product of A and B, and the kernel of the indicated isogeny is this finite group delta. Okay. And now let's try to figure out what this does for us in terms of congruences. Remember that I have an inclusion of T prime into a product of 2 Hecker rings. And what's happening here is that we're trying to figure out delta, which by definition is the intersection of T and T prime. Delta is the, well, it's the set of elements of T prime which become trivial when you pass to T double prime. Now, on the level of modular forms, it's quite easy to see what this decomposition represents. This decomposition represents, on the one hand, A is the subspace of forms coming from level n in the space of forms of level q squared n. And on the other hand, B is the orthogonal in the sense of the Petersen inner product. It is generated by eigenforms coming from new forms which do have a Q in the level. So the way to say it is that what you have here on J is an action of T prime. T prime is acting on the whole thing. And on the other hand, T prime acts on A through its quotient T, and T prime acts on B through the other quotient, the quotient T double prime. And in particular, let's say in words the following thing. The following thing is that delta is contained in the annihilator relative to T of this finite group delta. Well, why is that true? Okay. Suppose you have an element of T which, yeah, okay, so what is this thing? Let's go, let's give it a name. This is the kernel of the map from T to, well, it can be thought of as the kernel of the map from T prime to T double prime. It's the image in T of Hecke operators in T prime which are 0 in T double prime. In other words, it's the image in T of Hecke operators in T prime which die on B. So if you have something which dies on B, it will annihilate B intersect A, which is delta. So if you have something in, let's say, T double prime, which dies on B, it's going to die on the intersection. You have an inclusion like this if you think about actions of T prime. But on the other hand, T prime is acting through its quotient T on both of these modules. So this is basically a tautology, the fact that you can prove congruences to make delta, the ideal delta small is the activity of proving congruences. You can prove congruences by exhibiting some geometrical obstruction to J being a product. To say the thing in a very coarse way, suppose it were really true that T prime were the product of these two rings. Then the product decomposition, the idempotence in T prime, would force apart into two disjoint pieces any object that T prime acted on. And in particular, T prime's action on J would kind of rip apart J into the product of two abelian subvarieties A and B. And the fact that A cross B is not quite the abelian variety J, the fact that there's an isogeny there, is evidence that T prime is not the product of the two projections. And when you make that precise in group theoretic language, what you get is that this congruence ideal, which in fact is some ring conductor, is contained in this annihilator. So therefore, if you want to prove congruences, what you want to do is you want to prove that this annihilator is relatively small. In other words, to prove that the ideal delta is small, what you have to do is you need to prove that delta is big. And it turns out that it's not very hard, given the fact that you're allowing this map, which was previously diagonal, to be an injection. It's not very hard to compute delta. Well, let's just end with that. Probably erasing exactly what I need. But the point is the following. A was J0 of n cubed. And we had some inclusion, maybe call it iota for an embedding, of this abelian variety into J. And B was then the kernel of the map dual to iota, call it iota check in the language of abelian varieties. And since J is self-dual, we view the kernel of iota as contained in J, but also, in fact, since J0 of n has a canonical self-duality, it's also the Jacobian of something, iota check can be viewed as a map from J back to J0 of n cubed. And therefore, we know a lot about iota check. In particular, if you want to look at A intersect B, that is going to be, well, more or less, obviously, the kernel of the composite of iota check and iota, right? Because it's just the kernel of iota check restricted to A. And the whole point is that this intersection, well, notationally is delta. And on the other hand, iota check composed with iota is nothing other than a map. You know, where should we put it? Iota check composed with iota is a map from J0 of n cubed back to itself. So we can think of this as a 3 by 3 matrix. Of course, I'm not going to write down the 3 by 3 matrix. On the diagonal, you'll see Q and Q plus 1. And sort of filtered around through this matrix, you'll see Q's and T sub Q's. If you do it on some gamma 1, you may see some dual of TQs and some diamond bracket operators, but this is the general shape of it. And when you're done, you will discover the amazing fact that delta can be viewed as the kernel on one copy of J0 of n of a certain very simple Hecke operator, which I'll call T. Namely, T is nothing other than the culprit in this whole game. Namely, it's going to be a single copy of Q minus 1 times TQ squared minus Q plus 1 squared. It's exactly the number that we're looking for. And so this tells you that the annihilator of delta the annihilator in T of delta is just going to be the annihilator in T of the kernel of T. Of course, that will contain the ideal generated by T. And from that, it's very tempting to think that this annihilator is equal to this principal ideal. And that will give you the required statement that the ideal delta, the congruence ideal, is contained in T. There's one thing that you do have to check. You have to check that here we actually have an equality. And you can do that because you know how T is acting on the M-adic Tate module of J0 of n. Namely, it acts so that J0 of n is free of rank 2. The Tate module is free of rank 2. Also, it's isomorphic to its own ZP dual, if you want, because the T is Gorenstein. So you have a very good control over this equality, and you get the desired statement. So basically, that's the end of the proof. But I do want to say, without writing anything, that this activity of proving congruence in this way extends in a lot of different directions, and in particular has been pursued in one or more papers by Fred Diamond alone, 2 joint papers by Diamond and Taylor, a thesis of Kevin Buzzard, and probably other articles that escape me. Okay. Papers by